last class we looked at this experiment 3D HNCA, we were looking at that. We saw the peak pattern. We looked at see how the magnetization is actually divided from nitrogen into two pathways. One goes through the C alpha I, another goes through C alpha I minus 1. Now, because of that we get the chemical shifts, two types of chemical shift correlations. One is from between the nitrogen amide proton of residue I with residue I minus 1 C alpha, and the chemical shift of nitrogen and proton of I is correlated with the same residue I C alpha chemical shift. So, this is shown here again. So, this if you look at this particular slice which is taken at 130 ppm, we can see there are two chemical shifts for a given amide proton and a nitrogen chemical shift value. So, this amide proton could be somewhere 8.5 or 7.5, that and these together correspond to one amino acid which is shown here as I, but along this dimension C alpha here we are getting two peaks. So, the question which comes to our mind is how do we know which is I and which is I minus 1 C alpha. This is what is shown here, and that is something which is not easy to know directly looking at the spectrum. So, we therefore need to somehow distinguish or discriminate the chemical shift of I and I minus 1. We should know which is I and which corresponds to I minus 1. So, for that we need another 3D NMR experiment 3D HNCO-CA. So, we will look at that experiment now. So, as I said there are about 6 or 7 important NMR triple resonance experiment which we will be looking at this in this course. So, the third experiment now, the triple resonance we are going to look at is 3D HNCO-CA. So, what is the advantage of 3D HNCO-CA? Let us have a look. How does it, what information do we get? So, in a 3D HNCO-CA we correlate the chemical shift of nitrogen amide proton of one residue I to its neighbor I minus 1 C alpha chemical shift. So, you can see this is exactly complementary to what we saw in the HNCA case. In HNCA we correlated this with this to this and this, okay. But in this experiment HNCO-CA we are exclusively going only to I minus 1, we are not going to self. And how is that getting done? And that is getting done, or that is being carried out by exploiting this coupling values. So, if you see carefully here, this structure, that is NCO-CA, it does not exist here, it is NCA-CO and this side is NCO-CA. So, very interestingly this is not the same as this part. So, if I transfer the magnetization from N to CO, the magnetization will flow only to CO, only here, it will go only this direction, it will not go this direction because this CO coupling is very weak. So, N to CO as I mentioned cannot be transferred like this because it is on less than about 1 hertz, whereas this is 15 hertz. So, that is pretty strong, and I can tune my inept delay to go exclusively or selectively to this side. Now, once I go here, I can further go to the next atom by simply using this delay or this coupling which is 55 hertz. So, you have to keep these coupling values in mind, and this is about 55 hertz. So, if I have another transfer, I can actually exclusively go to this part. So, by doing that I am actually flowing the magnetization from Hn of a residue I to N of residue I to C alpha of I minus 1. So, to just remind you again, this is complementary to what we saw in HNCA, where we got both these chemical shift correlated to these two, but here we are correlating only the C alpha of I minus 1 to this pair NH. Okay. So, let us see how can we think of this as an analogy. So, the question is why this CO is in a bracket, you see here it is not shown separately, it is in a bracket. So, this is analogy I normally give is imagine that you have a train which passes through different stations, but let us say it does not stop at this station C, it passes through C but not stopping. So, it goes via C while coming forward, going forward, and backward again it goes through C, but it does not stop. So, we can now correlate this picture with this here, how by correlating or thinking of A station as a nitrogen A as amide, let me change this is H and this has nitrogen. Okay. So, I go from proton, this proton, I go to nitrogen, then I go to carbonyl, but you see I am not stopping here, I will not do anything to this nucleus, I will not evolve this nucleus, but I will transfer to C alpha and C alpha will be evolved. Then while coming back again I will come here, but I will not do anything to this nucleus, I will just simply come back using inept, I will come back using inept, but I will not evolve this. So, when I do not evolve this chemical shift, I have no information of the chemical shift of this. So, therefore, we put that in brackets. So, I am using that CO as a relay station. I am going through that, but I am not actually stopping there. Magnetization from nitrogen is flowing, is going through CO, but actually it is only going because it wants to go further to C alpha and it does not want to stop there. Okay. So, this is the analogy you can think of. So, any experiment in which you use a nucleus to as a stopping, as a not a stopping, but as a relay nucleus, so that you can go from one side to another side, that is put it in brackets and that is not evolved in chemical shift. Okay. So, this experiment is actually a 3D because it is correlating the chemical shift of amide proton with amide nitrogen with Ca. So, CO does not have any chemical shift value in this spectrum. Okay. So, 3D HNCA correlates of Ca I and I minus 1, whereas 3D HNCO correlates only to I minus 1. Okay. So, let us see how this experiment is designed. So, this picture is shown here again, the magnetization flow. The magnetization flow happens from amide proton to nitrogen, nitrogen to CO of I minus 1 now and then C alpha. So, basically you can think of it as crossing the border. So, this has a border here, dotted line is a border of amino acid I and I minus 1. So, the magnetization actually crosses the border, goes to the previous carbonyl and then further goes to the next station C alpha, takes the chemical shift value of this and comes back. So, this is what is shown here in this picture here on the diagram on the right. So, we will look at that now. So, you start again from proton amide, excite the amide proton, which is, as I told you, is always done with using inept. We transfer it to nitrogen according to by tuning it appropriate J value. Then from nitrogen we use inept to go to CO. So, if you recollect, this part actually is similar to HNCO. HNCO we did the same thing, we went from proton to amide, amide proton to nitrogen with inept and then from nitrogen again we went to CO for inept. But now there we evolved the CO chemical shift, but here see we do not evolve the CO chemical shift, we directly go to the next atom by a simple CC transfer module, and this some module is nothing but like a cozy transfer, like in cozy in proton they transfer by just J coupling, because these are homonuclear, remember this is both are carbon 13. So, this is a homonuclear CC transfer and that depends on the coupling value. So, we have to tune it to the coupling of these two nuclei and the coupling constant for these two, if you remember, is 55 hertz. So, 1 over 2 times 55 hertz if I use, I can go from CO to Ca. Then we evolve the Ca chemical shift. So, we are now capturing the Ca chemical shift and that is captured as cosine or sine omega Ca T1. Okay. And then you go back all the way. So, this is now the job is done. Now, you have to go back to the original proton. So, for that going back again you go back first to CO by CC transfer here, it is exactly the same now, it is going to be the reverse. Then from CO to N you go by reverse inept, and in nitrogen once you come you can now capture the chemical shift of nitrogen, because we need chemical shift of nitrogen that is evolved during this period, and then you go to proton by reverse inept and finally detect the carbon hydrogen chemical shift, and that is your direct dimension. So, now you can see the 3 chemical shifts what we have got here. We have correlated or we have connected the chemical shift of amide proton to nitrogen to C alpha of I minus 1, that is important to remember. Now, if you look at the peak pattern, what kind of peak pattern do you get? You see this is similar to what we saw in the case of HNCO. But here now this axis, I am sorry, this is a mistake here, it should be Ca, because we have not evolved the C alpha CO chemical shift, Ca is what was evolved. So, this is Ca dimension. Okay. So, for every slice here I am getting only one peak, and what is that chemical shift? That is a Ca of I minus 1 for a given nitrogen. So, let us go further and see. So, look at this again HNCA. If you look at the HNCA spectrum, we saw that we get 2 peaks in the Ca dimension for a given amide proton and a nitrogen combination. So, this is one amino acid. For each amino acid we will get 2 peaks, one corresponds to I and I minus 1, and we also noted that we do not know which is I, which is I minus 1. That information was not given, is not available from this spectrum. So, therefore, we did this experiment HNCO-Ca, which helps to distinguish the self means I, residue I here, from I minus 1, which is called sequential. How does it do that? Look at this here. So, you can see this is the 3D HNCO-Ca spectrum, which is what I showed in the previous slide. We have taken a slice of that for the same combination. You see, this combination should be same as this combination. That means, if this is 8.5, so let me write down this here. Suppose this is 8.5, this should also be the same 8.5. So, at the same location of this and this, I am getting now only one peak. So, now if I compare this strip with this strip, I can now match the two strips, and you see I can see the line here, you can see the line. This now tells me that this corresponds to I minus 1, because this experiment, this spectrum exclusively gives me only I minus 1, whereas this spectrum gives me both I and I minus 1. So, by comparing these two in a computer, I will be able to distinguish which is I minus 1, which is I. So, in this case it turns out this peak is I minus 1, because for the same strip, same combination of these two values, the same amino acid I am getting now this as I minus 1. So, remember again, let me write it more explicitly. This is residue I, this is residue I, this is residue I, and this is also I. For a given residue I am getting now I minus 1 in this case, and I minus 1 in this case. So, one has to therefore understand this carefully, that the combination of HNCA and HNCO-Ca helps me to distinguish a self peak from a sequential peak, and this is very useful for us when we go to assignments of proteins in the second half of this course. So, I would suggest to read this carefully, understand this carefully using the different textbooks that was recommended. So, let us move on to the next experiment, which is 3D HNCA-Cb. This is a very useful experiment for assignments, and it will build on our knowledge from HNCA. So, we have seen what is an HNCA experiment. So, as the name suggests, we are going one step further, and we are going to correlate C beta and C alpha to N and H. So, there is nothing in brackets here, if you notice carefully. Remember, if you have something in brackets, then it becomes that nucleus is not evolved in chemical shift, but here we are not, we are here evolving all of them. So, this is a HNCA-Cb experiment. Let us see how this works. So, this is how it is done. So, you have a nitrogen amide and amide proton and a nitrogen. So, similar to HNCA, we transfer the magnetization here. From here it flows in the both direction, like we saw in the like analogy to also a river. The river splits into two pathways. So, here the magnetization flow like a river splits into two pathways. One goes to C alpha, which is the same amino acid I. So, this is going from I to I, and this is going from I to I minus 1 directly. And from here in HNCA-Cb, we go one step further, we take it to C beta, and we also take it to C beta here. Okay. So, this is the additional step compared to what we saw in the HNCA case. In HNCA, we did not go to C beta, we stopped here and then we came back to nitrogen, but here we will go one more step extra, so that we get this chemical shift also in addition to this chemical shift. So, we are getting more information in HNCA-Cb compared to a 3D HNCA. So, it is a useful experiment because we get this very important C beta chemical shift also information for a 2 amino acid neighboring amino acids. Okay. So, let us see how this experiment is constructed. So, this is what I should write as CaCb. So, this is HNCaCb correlates chemical shifts of NH of residue I with C alpha and C beta of residue I and I minus 1 both. Okay. So, this is how the spectrum now will look. This looks slightly complicated compared to what we saw. So, now you can see here this axis is both C alpha and C beta, because we have detecting both of them in one of the dimension. So, earlier we had restricted only to C alpha. So, if you recollect, we C alpha chemical shift range was given as 43 to 68 ppm, but C beta has a longer range, we will see that shortly. So, how does the peak pattern look? So, what you see now, look at this here, for every slice or every strip or every peak for a given amide proton and nitrogen, for example, if I look at 130 and suppose this is 8.5 which I shown in the last slide, you can see that corresponds to 1 amino acid. So, for every amino acid I, you will get 4 peaks in this axis, and these 4 peaks correspond to C alpha I minus 1, C alpha I, C beta I, C beta I minus 1. Why we are getting 4? Because 2 are from here. If you look at this picture this side, 2 are from the I and 2 are from I minus 1. Okay. So, 4 together. Now, one good thing in HNCaCb is the color, the peak pattern, the phase of the peak, the color in the spectrum, real spectrum will be the C beta will have a opposite phase, mean if I make this as positive, they will appear as negative in the intensity, or I can say this is as a red color, if I display in a blue color, it will display me in a different color. So, this is just a display thing, but the point is that the C alpha chemical, the peaks corresponding to C alpha of both I and I minus 1 have one particular phase or one particular intensity, but this will be opposite, negative. If you call this as positive, this will be negative. If you make this as negative, this will become positive. So, C alpha and C beta therefore can be distinguished, but the problem of distinguishing C alpha of I and I minus 1 still remains, because these are coming in the same color or same phase, that I cannot distinguish, that we will see how to do that shortly. Similarly, here C beta of I and I minus 1, they have the same color, I cannot distinguish between these two, but there are ways to do that which I will show you. But in general, total number of peaks now coming for a given strip, there are 4. So, what is the chemical shift range here? What is the values we are looking at? So, that is given here. So, for a C alpha that we saw already, this is 43 to 68, and C beta now is a bigger range, it comes in 2 parts, 2 zones, 15 to 45. So, you can say this starts from 15 goes up to 45, and then between 45 to 63 normally you do not get any C beta, very rarely you will see, okay, and that now is C alpha region now, more or less. Slight overlap is there between C alpha, because some isoleucine, valine, proline, C alphas come below 63, they overlap with the C beta of some other amino acid such as serine and threonine. So, this zone 63 to 70 is typically for serine and threonine, these 2 amino acids, whereas all the other amino acids come between 15 to 45. Okay. So, now this although they overlap slightly here, there is some kind of overlap, but still the color is, as I said, the phase of C beta is opposite compared to C alpha. So, in a way you can distinguish still which is C beta, which is C alpha, even if they come in the same region, but more or less you see there is a regions exclusively for C alpha and exclusively for C beta. Okay. So, now this experiment is built like this. So, this, as I said, is a very complicated experiment, but idea is simple. This is, if you have understood how an HNCA, HNCOCA and HNCO, these 3 experiments work, you will understand this as well. So, this is more closer to HNCA. So, in an HNCA we saw that you start from an amide proton, you go to nitrogen 15, the same amino acid I with the inept, then we saw that the magnetization splits into 2 pathways. So, same thing happens here, it splits into 2 and the 2 are 1 is I and I minus 1. Now, here further what we do is we add a CC transfer step like in a standard COSY, homonuclear COSY. So, why you do that? Do that because we can go to C beta now, the next atom. But you see, as I showed you in COSY in the 2D NMR part, we can never go 100% to 1. We can try to go if we use a specific delay value, but we normally use a delay value such that it remains on itself this and something relays 50% goes to C beta. So, about 40 to 50% goes here and remaining 40 to 50% or 60% remains here. Okay. So, that depends on the delay period what you use, but normally we use a delay period such that there is a 50-50 transfer. Similarly, the I minus 1 use the same concept, it will also go to, it will keep some magnetization in on its own here like this, and some 50% will go to C beta of that amino acid I minus 1. So, now at the end of this step we will have 4 atoms sitting in the or excited by the pulse, and they will be all in the XY plane after this transfer. So, now we excite, once they are excited we can evolve those chemical shift for these 4 and each are independent. So, each of them will now independently evolve as different chemical shift. Okay. So, this is one pathway going independently of the other pathway, which is this pathway. So, these are 4 different pathways flowing independently. Okay. So, you can see now here that now I have independently 4 chemical shifts. Now, I reverse the whole operation, I go back to my original proton. So, how do I go back? I put the same transfer element, transfer step what was put here. So, it goes back into C alpha. So, whatever 50% came from here to here, it goes back. Similarly, what came from here goes back again, it is 50% of 50%, we will not go into detail of that, but this goes back into C beta to C alpha. Similarly, these two which have come originated or come from here, they merge again back into the C alpha I minus 1. Once these two have come, we use another reverse inept to go to N15. So, we are reversing this whole process here, and then here we evolve the chemical shift of nitrogen because we need that value, we need that chemical shift, and once we evolve that goes as N15 I T2. Remember, we are considering an amino acid I. So, this is I. So, I can actually write here to be more clear, this is I, this is I. Okay. So, from I we are splitting into I and I minus 1, and from I minus 1 we are coming back to I. So, this is again residue I, and then finally we get the residue, we go from from nitrogen we use another reverse inept and we come to proton, and that proton, this is we come by simple inept concept, and then that is what is detected finally as a in the 3D. Okay. So, this is the final detection period, and there we capture the proton chemical shift. So, you see now we are correlating many chemical shifts. So, let us see this carefully. So, we are correlating one pathway. So, each pathway is one type of chemical shift correlation. So, let us start from this pathway here on the leftmost pathway, that is which is flowing like this arrow is showing, and in this pathway we correlate this chemical shift amide with nitrogen with C alpha. So, this is one peak. The second peak is this and this combination. Third peak is this combination, this amide proton correlated with this nitrogen to C alpha minus 1. Then finally, C beta minus 1 and N I and H I. So, this is what I showed you as 4 different peaks. Each peak is basically one pathway. So, I can say this is C, let us say if this is C beta I minus 1, this peak is coming from this pathway. If this is C beta I, this is coming from this pathway, and this is C alpha I, it is coming from this pathway, and C alpha I minus 1 comes from this pathway. So, for a given H I N I combination, I am getting these 4 chemical shift value. So, this is how an HNCACB works, that for a given amino acid HI and I am able to get 4 different chemical shifts. So, this is a lot of information, very useful for us for protein assignments, as we will see later on. But now the question remains is how do I distinguish all this? So, one thing is, as I said, the phase, this phase will be different compared to the phase of the alpha. So, we just color it differently. Okay. So, in this spectrum, but we still have this ambiguity that which is alpha I and which is I minus 1. So, this is what is shown here. Similarly, we do not know which is beta I, which is beta I minus 1. Okay. So, therefore, this confusion is similar to what we saw in the case of HNCA CB sorry HNCA 3D HNCA. We had the same problem that we could not distinguish those two, we could not distinguish. So, what did we do in such cases? We took another experiment. So, similarly here we now need another 3D experiment, which brings us to this experiment. Either you look at this or this, both have the same information. So, now I will show you this 3D HNCO CACB, which gives me a complementary information compared to what you get HNCACB. So, combined together I will be able to distinguish. So, let us start from HNCO CACB. How does that experiment work? So, you can see this is similar to now HNCO CA. So, if you recollect HNCO CA, we went from HN, we went from CO to CO from N, and from CO we went to C alpha, but here now we are going one more step further and we are getting the chemical shift of C beta as well. So, you see this is a longer transfer, we are going longer and longer compared to what we did in HNCO CA, but we have to go longer because we need to get the chemical shift of beta. But again look at this here, it is exclusively selectively going to the I minus 1, it is not going to I, because NCOCA does not exist here, it is NCACO. So, therefore, this transfer happens exclusively from I and it crosses the border, this is the border here, and it crosses the border, the magnetization, and goes to the neighboring amino acid. From neighboring amino acid it goes to C alpha, and from there it goes to the C beta station, you can think of it these as stations, then it comes back. Again if you look at this here, we have put this in brackets, and that means that actually I do not get the chemical shift of this, but actually I will get all the other chemical shifts. So, this also can be put it in circle because I am getting a chemical shift of that, okay, but I do not capture the chemical shift of C alpha sorry CO. So, it is put it in brackets here. Okay. So, let us see how that experiment now works. This is the same picture which was shown in the previous slide. We are going from HN to CO to CA to CB. Now, in this 3D experiment is very same as HNCACB in terms of the axis, but now if you notice we are not getting 4 peaks here, we are getting only 2 peaks. And why is this 2 peaks here? The 2 peaks are basically corresponding to only C alpha I minus 1 and opposite phase again for C beta. So, C alpha C beta are opposite in phase here as well, but for a given amino acid I, if I call this as I, and a given amide proton I, let us say this is 8.5, this is residue I, for these I combination I am now getting I minus 1 chemical shifts of C beta and C alpha. So, this is the beauty of this experiment, that I am able to only exclusively get I minus 1 from here, whereas in HNCA I was getting both. So, you see HNCA CB and 3D HNCO CACB are complementary and they are needed together. Chemical shift wise is the same, the C alpha always remains in this range, this does not depend on experiment, it is the inherent nature or the range of C alpha. Similarly, C beta also always remains in this range. So, now we can see here the question we asked is how do we distinguish C alpha from C alpha I minus 1, which we could not, similarly beta from I and I minus 1. Now, with this experiment HNCO CACB I am able to do that, because now if you look at this same combination. So, these are both I, this is I, this is I and this is I. So, for a same I amino acid I am able to get I minus 1 here, whereas here I got only I mean I got both I and I minus 1. So, if I draw a line, you can see this line here, it is matching with I minus 1 here. So, based on this combination, if I keep these two spectra side by side, or these strips if I keep them side by side in my computer, I will be able to figure out which two correspond to I minus 1 and which two corresponds to I. Now, when this is I, then the positive phase will be C alpha and the negative will become automatically C beta. So, we look at this combination of positive negative for C alpha and C beta, and we look at the combination of HNCO CaCb and HNCaCb for distinguishing I from I minus 1. So, in this manner we can actually separate two residues I and I minus 1. We will go in the next class to more 3D experiments. Before we wrap up the 3D NMR part, we look at some experiments how to assign the side chains which are very important. So, right now if you recollect, we have only looked at backbone NMR chemical shifts of N, Ca, Cb and Co, but we have to now look at how side chains are assigned. So, in the next class we will continue with 3D and finish it with some side chain 3D NMR experiments.